Alright, here in this video we're going to look at the Chapter 1 test review. So I'm going to use the answer key for this video to help speed up so where you're not just watching me write. But I'll go over the description for each of these problems using the highlighter tool. Section 1.1, we are writing expressions. Number 1 says 4 times a number. Here's 4 times a number. You could pick any variable I just chose in to be the number. Increased by 7, so that's addition. Number 2, 8 less than. That's telling us to do subtraction, but it must come last, because if you think about, if you scored 8 less points than the other team, you'd have their score first, then you'd subtract 8 to find yours. You wouldn't do 8 minus, because that wouldn't make sense. If they scored 50 points, you wouldn't do 8 minus 50, because that's not the right order. So anytime you see something less than like that, that's prompting you to do the subtraction second. Like I had 8 less points than them, so their points first, then subtract 8. 3 and 4 is the same concept, except bringing in an equation. You don't have to say 8 less than a number right there. You could have said a number subtract 8, the difference of a number and 8. All those work. This one here, I used sum. You could have said added, any of the words that mean addition. For 8 and 3 times a number, and is equal to, you could say is equal to, if you wanted, 5. Here on this section here, we're solving different types of equations. So I'll highlight some of those. You'll see that I do my answer check for just the first one to remind you how that works. We check answers by, once we find the answer, substituting it back into the original equation, making sure we get a true statement. But on these, we're just doing the opposite of the different steps to see what our variable is. So on number 5, let's subtract 2 from both sides, then divide by 4. For 6, I've got variables on different sides of the equation, so I have to move those with addition and subtraction, which is why I chose to subtract x from both sides. Really on this, the goal is to get all the variables onto one side and all of the constants onto the other. And then here I divided both sides by 4 and simplified that fraction to get 1/2. On number 7, these variables are on the same side of the equation, so we do not move them with addition and subtraction because they are like terms. Like terms when you're on the same side. So that's what's going on here with this 3t and t. Now I subtract 3t from both sides to move the other one over, but the 3t and t are like terms, so they must be added together. If you did something like subtract t, you are wrong, because we have to combine like terms when they're on the same side. Here we see another set of variables on both sides, so I move them with addition and subtraction. And if you're wondering, would I get the same answer if you did it to where you gathered the variables on the left and the numbers on the right? Yes, you would get the same thing. You would have ended up getting negative 5b is equal to a negative 22. When you divide both sides by the negative, it would cancel out and give you the same answer. Here, variables on different sides again. Move them with addition and subtraction, and solve using the steps. Here we have like terms of constants, the 20 and the 6. So we put those together as like terms, not using addition and subtraction. As far as like plus 6, that would be wrong, because they're on the same side of the equation. So we just combine them as like terms. Here we have a situation where we have a's on the same side, but we need to put them together. But this one has a denominator. So what I'm doing here is I'm getting a denominator set up for this one so that I can add them together. Because I need to do a subtract 2a over 5. So what I chose to do is to get this a over 1 to a denominator of 5. So here is my a, because 5a divided by 5 is just a. But now it has common denominators, so that I can do 5a minus 2a to get the 3a. Now notice how nothing happened on the other side where that 3 is, because I didn't do anything in terms of, adding 2a over 5 to both sides or anything. I just combined like terms. And once I did 5a minus 2a to get 3a over 5, then I multiplied by the reciprocal on both sides, and that allowed me to get 15 over 3 to get a is equal to 5. Another thing you could have done on this problem is you could have multiplied the whole entire problem by 5 to begin with, and that would have given you 5a minus 2a is equal to 15. 3a is equal to 15 to get that same answer. That's probably the easier way, honestly. Here we have the like terms, variables on the same side, and then variables on the other side to bring over to get n is equal to 5. These here are the literal equations from 1.1. These can be a little bit tricky. We're solving for the variable that they ask. These get a little tricky because nothing cancels out or goes away. We just move terms around. So we're just moving terms with addition, subtraction, multiplication, division to help get the variable that we want all the way by itself. So on 13, they wanted us to solve for p. So we had to look and recognize that p is being multiplied by both r and t. So the opposite of that is to divide both sides by r and t. Cancels out r and t, getting p by itself, leaving this as the answer for what p is equal to. And this is the exact same formula as the original equation. It's just now been solved for p. For 14, we're solving for x. So you can see that x is with a 1/4 and it's with a subtract 12. So I did the adding 12 to both sides first. Then I multiplied everybody by 4 to get x by itself. Distributed the 4 here to get 4y plus 48. Here for 15, we're asked to solve for y. Y is being added with an x, but all of it's being divided by 2. So I fixed that first by multiplying both sides by 2. Then we have 2a is equal to x plus y. I subtract x from both sides, and there's the answer. So once again, this is the exact same equation as that, but rearranged to be solved for y. 16 is more complicated of one that I would give on a test. We're trying to solve for h. I could look in here and see that h is being multiplied by a 2, a pi, and an r. So I could divide that by everybody, because remember when we do division, we have to do it with everybody. And it also helps cancel out a lot of terms from the second one. So after I divide everybody by 2 pi r, we get to right here. And then the only thing that's with h is an r. So I'll subtract r from both sides to get that final answer. 1.2, we are solving inequalities. It's just like solving equations, except if you multiply or divide by a negative number, we have to flip the inequality. So you can see here, to solve for z, z was being divided by negative 4, so I multiplied both sides by negative 4, which does cause the inequality to flip. So then I had to graph z is less than or equal to negative 8. So remember that there's a line under your inequality. It's a filled circle. And then we discussed a couple ways to know which way to shade. You can do less than, if your variable's on the left, you can shade the way the arrow's pointing. But we also talked about just testing out numbers. So if I am looking to see my variable is less than negative 8, and I pick a number, such as negative 9, I see that negative 9 is less than negative 8, which means I need to shade towards the way that worked. And if you test a spot such as negative 7, you'll see that it's not true, which means that I would not shade towards the negative 7. Here on 18, we solve the inequality to get a is less than or equal to 3. So that's a filled circle on 3, shaded to the left. You have a couple more inequalities. When you solve this one, we get 4 is less than q, which is the same thing as q is greater than 4, if you want to flip it around using the symmetry property. That's an open circle because there's no line under my inequality. And I need my variable to be greater than 4, so I'm shading all the numbers greater than 4. Here, we end up with 2 is greater than n, or n is less than 2. Open circle, shading to numbers less than 2. (1.3) was about using the slope formula, y2 minus y1 over x2 minus x1, also known as rise over run. So here you can see me using my formula in the coordinate points. Here's my y2, here's my y1, here's my x2, and here's my x1. When I use this formula, it'll tell me the slope between those 2 points without having to count on a graph. When I do the slope formula for number 22, you'll see here that I get the slope is equal to 0. You might say, well, hey, I got this, 0 over negative 3. Why isn't it undefined? An undefined slope is when the denominator is 0. The numerator is 0 is fine for slope. That just means we have a slope of 0. It means we didn't go anywhere up or down, but we traveled some left and right. Think about walking in a hallway. If you travel left and right, but you don't go anywhere up or down, you're walking on a slope of 0, a flat ground. So it's not undefined. This slope's equal to 0. And then when I do the slope formula here, we get the slope's equal to negative 2. You can determine slope from a graph by just counting rise over run. Always recommend starting with your point on the left. That way your run is always positive. So to get from this point to this point, because we want to check it with whole number intersections, so you look for spots on the graph where it crosses over an intersection point, and then you count rise over run. You could also use the slope formula on these 2 points. You'd get the same answer of a slope of negative 4 over 5, but this was showing that with a graph, you can do rise over run and count it yourself. So here I am counting rise over run. Let me go back and see here. Looks like somehow this got off. So let me redo it. I'd go from this one to this one, which is still the up 1, 2, 3, 4, 1, 2, 3. I don't know how my drawings got off there. Happened on that one too. So here we'd have a whole crossover. Here's a whole crossover spot. Up 1, slope of 1, 2, 3. To get that rise over run is 1/3. Now we'll use that sum potentially when we're looking at 1.4. 1.4 used two things. Slope intercept, y equals mx plus b, point slope. Y minus y1 is equal to m times x minus x1. Notice that both of them have slope in it because both of them are talking about lines. So it says find the slope and y-intercept of the following line. This line right here is not in y equals mx plus b form, nor is it in point slope form. So I went ahead and switched it over. Now, and we can see this sometimes too. We wanted to get this guy into y equals mx plus b form. So essentially I need to solve for y. So notice what I did. Got rid of my x term by moving it over with subtraction. And then we needed to divide everybody by the number that's with y, which was -4. And when we did that, here we are in y equals mx plus b, to where this is the slope. So there's my slope of 3/4, and there's my y-intercept. And y-intercepts as a coordinate point are always 0, then that number. In this one, they give us the slope and the y-intercept. And I went ahead and had us do it from both perspectives just to get us comfortable with this. But really all I'm doing here is I'm filling in, and we'll do this on some other ones too. Point slope, which is y minus something, is equal to m times x minus something. And we fill in these spots. We fill in the other y-coordinate, we fill in the x-coordinate, and we fill in the slope. So notice what I did here. If the y-intercept is 3, my coordinate point is 0, 3. So there's me filling in the x-coordinate. There's me filling in the y-coordinate. There's the slope. Now there's two ways of finding slope-intercept. One way is to distribute the -4 here to both spots, and then add 3 to both sides. And you'll see that I get -4x and then plus 3. But this one, they already told us the y-intercept, so we could have just done y equals mx plus b, filling in our slope and our y-intercept, which was -4 and 3. So here, they didn't give us a slope, nor did they give us a y-intercept. And we know that because, and if they give us a y-intercept, it has to be 0, something. Neither of these points are that. So I need to use the slope formula to find my slope. So I use the same formula that I would have from 1.3. And I went ahead and I used the highlighted point to fill in point slope. So what I did is I filled in point slope using slope of 2, and then this coordinate point. So then, to find slope-intercept, all I did was I took my point slope and I solved it for y by distributing the 2 and then adding the 6 to both sides. These guys are the exact same equation, just in different forms. So this one is just having us use our knowledge of parallel and perpendicular lines. For this one here, you will see that we've got parallel to this line. So the only bit of information we need on this is the slope. We don't care about the y-intercept because we are parallel, which means we need the exact same slope. So that's why my slope here again is at 9. They tell me the y-intercept's at -2. So our equation has the identical slope of -9 and the y-intercept that they gave us of -2. This one, it tells us a point to pass through and that we're perpendicular to this graph. The only thing we need from this is the slope. We don't care about its y-intercept, because perpendicular is when you have opposite reciprocal slope. So opposite means the slope here was negative, so ours is positive, and the slope here was 1 over 3, so ours is 3 over 1. So I then used point slope, filling in our missing values. I used our slope of 3, and I used this as my x1 and y1 with point slope here. Once I had that, I then distributed, subtracted 1 from both sides to get that equation for my final answer. And that equation is perpendicular to that. You can see, because the slope was negative 1/3 to ours being positive 3 over 1. And then we also now have access to what our y-intercept was, which just came about from us solving this point slope. In 1.5, we were graphing linear inequalities, which involved us using y equals mx plus b with our y-intercept and our slope. 32 is a horizontal line with a y-intercept of 1. You could really think of this as y is greater than 0x, so no slope, plus 1. It has no rise over run, that's why it's horizontal. It's a dotted line because there's no line under our inequality. And remember with y, if our inequality is facing y, we need bigger y values, so we're shading above. If our inequality is not facing y, that means we need smaller y values, so we'll shade below. (33) was already solved. It had a y-intercept of 2, a slope of up 1 over 1, a solid line inequality, so I drew a line and shaded below. 34, I needed to solve for y. I did that by subtracting x from both sides. Graphing a y-intercept of 4, a slope of down 1 to the right 1. And then since I had y as less than or equal to, I shaded below. 36, to solve for this y, after I subtracted 2 from both sides, I then needed to divide everybody by a negative 1 to get y by itself. That did cause the inequality to switch. So if you missed that one, that's probably why. But I had a y-intercept of 2, slope of down 1 to the right 1. Y is greater than, so I shaded above. This one has a y-intercept, but it's a y-intercept of 0, which is why I started here at the origin. Did a slope of down 3 to the right 1. Solid line because there's a line under my inequality, and I shaded above. (1.6). This is our systems of equations. So on this, the first section is graphing, and I show you the 3 outcomes that can occur. And this is after you get your equations solved for y equals mx plus b, you would graph them, and you're looking to see where the equations cross. On 38, they end up being parallel, so there's no solution because the lines never cross. 39, when you solve the second equation, you realize that it's identical to the first equation. That's infinite solutions. And more so, we call this in class infinitely many solutions. And then 40, when you solve both of those out, you get some equations that are going to cross because they have a different slope. This pink one here, you'll notice that the y-intercept is off of the graph, which will happen sometimes. And you could also scale this to make it work, but that gets a little tricky too. So I instead just talked about how to find some points. If 15 is my y-intercept, I know that 0, 15 is a point on my graph. It's off the page though. And then I started to do the slope of -3, which is decrease the y value by 3 and increase the x by 1. So I decreased by 3, increased by 1. Decreased by 3, increased by 1. Decreased by 3, increased by 1. And then eventually, those points started to land back on my graph. So I now have them plotted, and we can see where they cross over. 5, 0 is the solution because that's where those equations cross. For 41 through 43, there's different methods that we can use here: substitution, elimination. For this one, I chose elimination, and I decided that I wanted to cancel out my t's. To do that, I need them to be the same, but one positive and one negative. And when I looked initially, I saw that they were both positive t's. So I thought if I could get that top t to be a negative t, I could then use elimination. So I took this entire equation and multiplied it by -1. And what that did is it allowed for when I go to add these equations up now, the top equation turned into this right here, r minus t equals -5. When I added them up, the t's cancel, giving me -2r plus an r plus 1r. To get the -r is equal to 4 minus 5 to get the -1, and then solve for r is equal to 1. I can then substitute in r is equal to 1 into either equation. I chose the top equation, and I found my answer. This is where I always recommend double checking your answer, because it's very easy to make mistakes on solving these. On 42, I used substitution because I already had y was equal to something. So the way substitution works is you take what one variable is equal to, in this case, -4x plus 2, and you substitute it into the other equation. So I'm going to replace that y with -4x plus 2. When I do that, and I go through and solve, I end up getting that x is equal to -1/2. I then chose the second equation to substitute in x is equal to -1/2 and solved it out and found that y was equal to 4. On 43, I chose to use substitution, so I added 3y to both sides to get x by itself, that x is equal to 3y minus 12, and then I substituted that in, that x is equal to that right here. Solved for my y to get 5. Use my first equation to go through and just plug in y is equal to 5 to find for my x. If you wanted to see more on solving systems of equations, I have that whole video. If you go to the 1.6 homework and open that document, there's a video link attached in the homework. And you can use that link to get access to a whole other video about all the different systems of equations. (1.7). This is where we're graphing two inequalities at the same time, and the answer is the double shaded region. We don't care about where they cross over on these. Notice how I didn't care about that spot. I didn't care about that spot. Instead, we just want to see where would both of these be shaded. So for the green line, which you can graph with your y-intercept and your slope, you can see that I shading below for green and above, oh, and below as well for red. Both of these are less than. And if you look at the double shaded section, it's the section that's both less than the green and less than the red. You also could have done this here by shading everything below the green, everything below the red, and then you would see that that does in fact give you this as the double shaded region. For 45, you can see where I worked to find both of the inequalities in y equals mx plus b form. Both of them end up having their inequalities switched because we are dividing by a -1 on both of them. And then when you graph them, which are these guys here, I need to be below the pink line, but above the green, and we can see that double shaded region there. If you are level 5, that's the end of the review for you. We're now switching over into level 3 only content. So in 1.7 for level 3, we found the intersection points of triangles formed by systems of inequalities. We graphed them out on the calculator, or you could graph them on some graph paper. But if you take these 3 inequalities, you can find where they cross over. You can also do it by hand. And remember, when we're doing it, we really don't even think necessarily about them being inequalities to find the crossover spots. The inequalities do help us make the shaded picture. But right here you can see if we think of this here really as x is equal to -5, and I put that right here, and I'm subtracting a -5, 3 plus the 5 gives me that 8. So there's that crossover spot right there. And then I can use that right here as well, that this is really y is equal to 3. So if I put that there and subtract 3 from both sides to get a 0 for that x, there is 0 for the x, 3 for the y. And then for this last point here, these two guys would just cross right where they say. Y is equal to 3, x is equal to -5. But you could graph these out on graph paper if you wanted to find those same spots. You could do the pink line and the green line on your calculator and use second trace intersect to do it that way as well. So here we're in 1.8. We're graphing the systems of inequalities, finding our shaded region that encompasses all of them. On this first one, I set you up with a compound inequality, which you'll see sometimes. I kind of explain what this guy's doing right here. This is basically saying that x is between 1 and 5. So I went ahead and wrote these both out separately. You know, x has to be greater than or equal to 1. X has to be less than or equal to 5. And you'll see that sometimes if you're looking at like a weekly report, but maybe they only want to see Monday through Friday. So they say between, those 5 days. Remember that we do not graph the optimization function. He's just waiting there at the end. Now, when I graph these 4 inequalities, we get this picture. We get those intersection points right there. those are what you plug into the function. So what I'm doing is I took all 4 of those and substituted into this. So really 3 times the x value minus 2 times the y value. And when I do that, all of those yield different numbers, and you can see those numbers right there. Whichever one was the smallest, which was this point, is my minimum. Whichever one gave me the largest number, which is that point, was my maximum. Here, when you graph them, you find the crossover points. You can see where all the shadings overlap there in the middle. And when I plug those into their own optimization function, which is this time 4x minus y, they yield us different numbers. This point ends up being my minimum. This point ends up being my maximum. Because remember, it's always the vertices that we plug into this optimization function. You never have to graph that. Don't graph that guy. He's just what we plug in our points. This one, I recommend using your calculator to find that crossover spot by typing the red and the orange one into our calculators. And then we used second trace. And I believe it's option 5, which says intersect. And going through that. But we can certainly talk about that more in person if you need that help. Right, and then here is a optimization word problem here for us. Machine A can produce 30 steering wheels per hour at the cost of $8 per hour. Machine B can produce 40 steering wheels per hour at a cost of $12 per hour. The company can use either machine by itself or both machines at the same time. What is the minimum number of hours needed to produce 380 steering wheels if the cost must be no more than $108? Okay. So, I put on here, I'd recommend using your calculator to graph to find the intersection points, because they are a little bit tricky to find. This problem's pretty tough. The way I would break it down on the test is I wouldn't give you one like this because there's too many things that can go wrong as you're trying to find the right answers. So I instead kind of take the concept of this problem and break it up into a couple smaller problems to where there's one to where you're really just graphing and finding the intersection points. There might be one where I give you some points and you have to plug them into the optimization function. You wouldn't be expected to go start to finish on one complicated like this. The question, though, is what's the minimum numbers of hours needed? So that's what told me that my optimization function just needs to be A plus B. Hours on one machine plus hours on the other machine. We need to figure out what combination minimizes that setup. Then otherwise, here's my 2 inequalities. It's the amount that we need to produce, because one of the machines could produce 30 an hour, the other one could produce 40 an hour, and the prompt wanted us to create at least 380 steering wheels. So that's the amount inequality. And then this inequality is the money inequality. $8 for one machine, $12 for the other machine. And we needed the money to be less than or equal to 108. So to get these into our calculator, we needed them into y equals mx plus b form. But in this one, instead of doing x comma y, we were doing a comma b, which means this is the variable that I need to solve for. So on this one here, I subtracted 30a on both sides and then I divided everybody by 40, and it simplified to that. This second one here, I subtracted 8a from both sides, and then divided everybody by the 12 with the b, and it simplified to that. Now, these two inequalities are there just to limit us to the first quadrant. Always be on the lookout for those in the word problems, because we can't have negative amounts of steering wheels produced. When you graph all four of those guys, you get these intersection points. This one representing if I used only one of the machines. This coordinate point representing if I used only the other machine. This one here from your graph ends up being using both of the machines at a certain rate to one another, which ends up being 6 hours on one machine, 5 hours on the other. And when you plug these points into that optimization function, which was just the number of hours, A plus B, you end up getting this one's 13.5. That one's 30 over 8, which is almost about 12. But then this one was only 11 hours. So the answer to this is it's going to take 11 hours minimum, 6 hours on machine A, 5 hours on machine B. And if you run the machine for those hours, we made enough backpacks, we made at least 380, and we also kept the cost below $108. You do not need to do this 1.9. It's no longer on chapter 1. Don't need any of that. Don't worry about those. We didn't learn how to do those.